Good day. I am Edric Luis G. Ato of ID 121 and I'll be teaching ENGMEC3 long quiz number 2. The topics for today's video will be about shear stress and flexural stress in beams. So, let's get right to it. A rectangular beam 8 inches wide by 14 inches high supports a total distributed load of W and a concentrated load of 2W applied as shown in the figure. If FB or our flexural stress is maxed out on 1800 psi and FV or our shear stress is maxed out on 220 psi, determine the maximum W allowable. So, first let's draw the free body diagram here. So let's call this R1, R2. We have a uniformly distributed load of W and 2W concentrated load here. This is 3 feet or 36 inches. This is 9 feet or 108 inches. And this is 144 inches or 12 feet. First, let's get the reactions. So, taking counterclockwise as positive, let's get the moment at point 1. This would be equal to 0, and this is equal to W times 144 inches over 2, because this is where the centroid is, and this must be a negative value because it is going clockwise. Next, another clockwise moment would be minus 2W times 108 inches. And then we have a counterclockwise moment of R2 times 144 inches. We would get R2 to be equal to 2W. If we take the summation of forces along the y-axis to be equal to 0, this would be equal to R1 minus W minus 2W plus R2. Take note that W here is already the load, meaning it's already a force. So we could get R1 to be equal to 3W minus R2, it's 3W minus 2W, so it's simply W. Next, let us create the shear and moment diagrams. So first is the shear diagram. We start off at 0 and then we go up to W. Then we slowly uniformly go down to W over 4 around here. Then go down again abruptly to negative 7W over 4, uniformly go back down to minus 2W, and then go back here. So you can see we have two areas, A1 and A2. Take note that this W over 4 and negative 7W over 4 and negative 2W, these will be, you will get this through your creation of the shear diagram. So if you haven't mastered that yet, you may click the link in our, you may click on the video in our YouTube channel. So for area 1, this is going to be equal to 1/2 times 108 inches times W plus W over 4. Take note, we're using 108 in this formula because this is the area of a trapezoid. So we're going to get here 5W over 4 times 54, which is equal to 67.5 W. This is in pound inches. For area 2, this is equal to negative because it is below 0, 1/2 times 36 inches times 7W over 4 plus 2W. This is equal to negative, this is going to be 18 times 15W over 4, which is also going to be equal to negative 67.5 W pound inches. Okay, now that we know the areas, we can now draw our moment diagram. So we start off at 0 because there are no external loads or external moments. And then we go up to 67.5 W. This is in pound inches. And then we go back down to 0. These are second degree polynomials, by the way. So we have V max equal to 2W and M max equal to 67.5 W. This is in pounds and this is in pound inches. So how are we going to get the value of W? Well, first we could find the flexural stress. The flexural stress is just equal to M max, the maximum flexural stress, I mean, is equal to M max times Y over I. Now, how do we get Y and I in this case? If we use this rectangular beam, it says it's a rectangular beam. This is 8 inches, this is 14 inches, and the neutral axis passes through the centroid. Your I here would be equal to 1/2 base times height cubed. Let's not substitute any values yet because we might be able to simplify later, and your Y is for here. So this is going to be 67.5 W times your Y, that is equal to H over 2 all over 1 over 12 BH cubed. Now H could cancel out, this becomes squared, 2 and 12 cancel out, the 12 becomes a 6. So this becomes 6 times 67.5 W all over BH squared, and that should equal to your maximum flexural stress, which is equal to 1800 psi. So it becomes 6 times 67.5 W, or we could simply get W already. W would be equal to 1800 psi times B. Our base is 8 inches, our height is 14 inches, and square it all over 6 times 67.5. We're going to get a value of 6968.89 pounds. We could also look for the shear stress. It's equal to V max times Q all over IB. Now, how do we get Q here? Q is simply going to be V max times a Y. But this Y is not the same as the Y that we used for flexural stress all over IB. The I is still the same. The A that we're going to be using is, so that it could be maxed out, this area right here, so from the top to the neutral axis. And the Y that we're going to be using, if this is YC, the centroid of that area, the Y that we will be using is the distance between YC and Y. So this would be V max times base over 2, height over 2, I'm sorry, height over 2 times base times your height over 4. Why is it height over 4? Because this is your height over 2 and this is your height over 4. this is your AY divided by 1 over 12 is B H cube times B. So you could cancel B, cancel this H and H, so this becomes H times 1. And this becomes 3 if you cancel 12 and 4. This becomes 3 V max over 2 BH. And V max is going to be 2W. So you can cancel the 2. So it becomes W is equal to, this should be equal to the maximum shear stress, which is 220. So 220 times our base, which is 8 inches, times the height, which is 14 inches, all over 3, and we are going to get 8213.33 pounds. Now the problem is asking for what's the maximum value of W that we could use, and normally in this type of problem we're going to use the smallest value that we computed, because if you place this into our shear stress formula, we would actually get a shear stress that is less than 220, which is what we like because it's going to be safe and we are happy that it's safe. But if you place this 8,213.33 pounds in our flexural stress formula, we would actually get a value that's greater than 1,800, which is very sad because it is not safe. That marks the end of today's video. Thank you all for watching. You may also avail our syntax tutorials by scanning the QR code flashed on screen right now. Once again, this is Edric Luis G. Ato of Syntax, paving your way to excellence.